Good morning again. Today we'll talk on multimodal interaction. We look at different principles of combining different modalities of interaction together, and also different case studies where multimodal interaction found to be useful. So what is multimodal interaction? That when we interact with more than one input or output modality, so many times we do it intuitively. Say, for example, when you are talking on the smartphone and you are doing some screen sharing, you are simultaneously use your voice input for the communication and also your hand input or the touch screen for taking any task. Or when you are listening to the phone and at the same time the phone is vibrating to indicate you that there is an incoming message, there also you are combining more than one modalities together. So in our daily life, when we also do multitasking, so knowingly or consciously or unconsciously we process multiple modalities together, and our brain is very good in segregating this input. So and we process it in everyday communication. Although for doing it through a machine sometimes poses interesting challenges. And although as humans we can process multiple modalities easily, but when we are doing it consciously to control a machine or maybe a physical device, there are some challenges both from the human factors point of view and as well as from the machine processing side of point of view. So there are many applications of multimodal interaction, like gaming consoles are the most common one. Information visualization is an interesting example that you can, when they are, you can say, think about a Google map that you can zoom it at the same time if it is possible that it's also um, understanding your eye gaze fixation, or it's taking direct voice input, then we can do a much richer interaction with it. Automotive environment is an example that when we are driving, people can still take calls by talking to their phones. And although it is not allowed in many Western legislation, but many people also use their smartphone while they are driving. And similarly, in aviation also, pilots, they are ended up with a whole bunch of console and they are constantly talking to co-pilot or the air traffic controller, but at the same time they are interacting with various physical modalities. And we will also look at some case studies with assistive technology when we have to go for multimodal input, because the level of abilities of the, or the range of abilities of the person limits use of one particular modality, and we have to explore alternate modalities, more than one alternate modalities. So we look at case studies on each of these samples. So here are a few quick examples. So you may have seen it before, but just to show you the difference. So the first example is we are operating a robotic arm using both eye tracking and finger movement. And this is just a simple 4DOF robotic arm. And it responds to the eye gaze movement, that if the operator looks left or right, it moves left or right. And similarly, if he looks up or down, it moves up or down. And the similar thing we can also, exactly same interaction we can also do with finger movement. So a screen cursor, here the red blob is controlled by eye gaze or finger gesture, and here he is operating with finger movement. So if he points left, the screen cursor moves left, and the robot reads the screen cursor, and accordingly it takes one of the four-way movement. But here you can notice that we are not processing both modality simultaneously, or the robot, or, well, we are processing it simultaneously, but the instruction is given to the robot uh, of one of two modalities, not both together. So this is another example of eye gaze movement and sorry. So this is one example of both eye gaze and head movement together. So now I am moving the pointer with my eye gaze, and as the pointer is moving, one of the blue button is turning white, indicating that where we are trying to point. And here it's also integrated with some target prediction technology. And now I am putting a piece of cardboard in front of the eye tracker. So now automatically the system switches to head movement modality. So the system is continuously monitoring head movement and eye movement. So it's giving priority to eye movement. And when eye movement is not there, then it is giving priority to head movement, and I can seamlessly move between two modalities, eye and head movement. So in both this example, what you can see that it's something called redundant modality, that the same thing we can do with two modalities. So if one modality doesn't work, I can switch back to the other modality. And this is one example of multimodal interaction, that although we are in effect working with at any point of time with a single modality, but we also have available to us an alternate modality which is also doing the exactly same activity. So in this third example, what we will see, that we will move eye gaze and voice. So here it's a bit different, that we are using eye gaze for pointing and voice for selection. So the eye gaze is moving the screen cursor, and when it is on target, the operator can issue a voice command like select or go or something like that, and that will select the target. So here, unlike the previous two cases, that we are assigning different activity for each modality.
Start.
Go.
So the go command is selecting the target.
Go.
Map.
Go.
So here
East.
Go.
the operator is looking at a particular target and then uttering the keyword which is selecting target.
Go.
Dito.
Go.
Radar.
So in the final example, instead of eye tracking, we will use head movement and EEG. So here also it's like the previous case, that we have assigned different activity to each modality. So she is moving the screen pointer by head movement, and she is selecting it with an eye blink instead of this voice command. And the eye blink is detected through EEG. So we used the emotive weight electrode EEG tracker. So she is moving pointer with head movement, and when the pointer is on top of the target, she is blinking, or it's an exogenous blink or conscious blink, and that is selecting the target. So here also we assigned different purpose for different modalities, and they are working simultaneously to achieve a task. So these are maybe two of the main case of using multimodal interaction. That in one case we use redundant modality, that is the same activity can be done by multiple modalities, and we can switch between one or two based on our purpose or availability. In the second case, we assign different function to different modalities, and they work together or simultaneously to achieve a particular task. So what are the advantages of our unimodal systems? That many times it's easier to use and require less training, because in our everyday life we always do multitasking. Many times it's robust and flexible, that even one modality fails, the other modality can take over, and we can keep on working with that. Many times it's preferred by users because it looks more intuitive when it is implemented properly. Like you can think about when we use our smartphone, and a smartphone without the touch screen and a smartphone with the touch screen, that how the touch screen becomes so intuitive for us to use various features. It's many faster and efficient, and often we can add new functionality to it. and it can be applicable to many different environments and form factors that challenges UI, especially mobile phones. That for a laptop, I can attach a touchpad, mouse, and so on, because we have the space to do that. For a handheld device, we do not have the space to attach another peripheral device to it. So whatever is available in the screen state, that area we can use for various functionality, like the camera we can use for eye tracking, the screen we can use for touch screen and multi-touch system, and the microphone we can use for voice command, and similarly the we can also provide output through vibration along with the standard speaker output. So the multimodal interaction often helps us to reduce the form factor of device and user interface. Main challenges is that you may already noted that mismatch in latencies, although in these case studies we recorded it after spending quite a lot of time on developing on these systems. But many times all modalities, they do not work simultaneously, and as you may already know that many modalities like eye tracking, gesture recognition, they depend on camera based technologies, and these image processing, that takes time or takes unequal amount of time when we are processing a hand gesture compared to when we are translating or estimating eye gaze. And this mismatch in latencies can make one modality preferable to another modality, or also even during the voice command also, that we sometimes we face problem in terms of speech recognition, and that this mismatch in latencies can create an unnatural environment, and it can make it further difficult to use the unimodal system. And similarly, just like latencies, the inaccuracies of sensor is also similar, that I can move a mouse pointer a lot more accurately with a touchpad than I can do with eye tracking or head movement tracking. And if these modalities are not combined in the based on their based use cases, that users may get a very bad experience, that they always can prefer the standard modality over any alternate modalities for this inaccuracy. And same thing we can also talk about direct voice input, that if the voice command is not recognized well, users may refuse to use it. And then the simultaneous input and setting precedence, that when we have more than one input, that which input we will prefer, and it becomes further complicated when we are working with multiple users. So in the all previous 4 case studies, we have one person operating one single device, but as we move along, we will see that if we take a case study from a digital television where multiple users are watching the single television, then how to set precedence among multiple modalities, that say one person is issuing voice command and another person is working with the remote, that becomes challenging. And also the quality of multiple modal input output, that if the modalities are not combined properly, just as the previous 2 bullet points I mentioned in terms of latencies and inaccuracies, the experience may be worse than a unimodal input. And some example for it, you can see that even though the say a laptop can be used with eye tracking or finger gestures, but still we prefer to use it with a touchpad, or maybe by attaching a wired or wireless mouse to it, because we we are more proficient with using with a touchpad or mouse, and we do not the level of accuracy we get with eye movement or head movement is worse than what we get with finger movement or mouse or touchpad. So even though we can install programs for eye tracking based control or head movement based control on a laptop, we very rarely use it for our practical purposes. So how we can fuse multiple input or output modalities together, because it kind of decides that what will be the quality of multimodal systems. So there are various characteristics. So the first one is the time of fusion. That fusion can be classified into pre, mid, and post mapping with respect to the time of mapping raw sensor data into recognizable symbols. So it's easier to imagine, say you think about a gesture and speech recognition system. Okay. And it's same, you can also move it on to eye tracking system or our traditional mouse or touchpad based system. So what is pre, mid, and post? So the pre is that when we are fusing at the raw signal level. So for example, for a speech recognition system, the raw signal is the acoustic signal. For any eye tracking gesture recognition system, the raw signal is the image frames captured from a live video. Mid is that we say we are combining a eye tracking and gesture tracking system together. So we can take the video frame of the frontal part of the user, including both eyes and hand movement, and then we can decide that which we should process, that whether we should process the facial part for estimating eye gaze, or we should only process the finger part to track finger movement. Same thing we can do with acoustic signals also, or electronic other electronic signal when we have multiple modalities. Mid is that we did some intermediate level image processing, and I know that where the user is trying to look at, or I know what the user is uh, trying to utter, and there I am trying to fuse. And finally, the post mapping is I already mapped the user's intention into one device activity. Say, for example, mid level is that you understand that I am telling select, or you understand that I am looking at the screen, or I am blinking, something like that. Next is post mapping is that you decided or map this human action to a device response, that when I am blinking, it's mapped to the click action. When I am looking at a particular point of area of screen, I want to move the mouse cursor there, and then you are taking the fusion decision that whether the mouse cursor will be moved based on my finger movement or eye tracking movement. So that is the post mapping of fusion. Next is that what information to be fused, and very similar to the previous case, that information can be fused at the raw data level. That means that the basic image frames or the acoustic or electronic signal. At the feature level, that means that the relevant features extracted from the acoustic signals, maybe the phonemes or the image features, that the finger position or eye gaze position, or at the decision level. And then the type of cooperation among different modalities. So different modalities can coexist simultaneously, like our case study with this eye movement and voice command, or head movement and EEG signal, or one at a time, just like the robot case, that I can take precedence of finger movement over eye tracking. And finally, the method of fusion, that different modalities can be fused following rules or modeling them as a set of prior probabilities in a Bayesian model. So how we are actually simultaneously combine these modalities. So the last point we will further explain when we will take a automotive case study soon. So let us take the first case study, and this will mostly elaborate this last point, that about the methods of fusion. In this case study, we will look at this our automotive user interface, where we will try to operate the car dashboard using both hand movement and eye gaze movement. And we will look at three different ways to combine this eye gaze movement and hand movement. This video demonstrates combining eye gaze and finger movement tracking technologies together in an automotive environment. In this study, the participants' primary goal was to drive the car using the driving simulator. When she heard an auditory cue, she tried to select a target on the secondary screen, which was not a touch screen. We tracked her eye gaze movement while she glanced towards the display and enlarged target on the secondary display following her eye gaze. While she stretched her finger towards the display, we also tracked her
finger movement and combined it with her eye gaze movement using a Bayesian model. The model was used to predict her intended target, and the intended target was automatically selected.
So the objective is exploring use of non-invasive gaze-controlled interface and finger tracking technology, and comparing different multimodal fusion strategies, so that it's when the user is strapped to the seat, he or she may not reach to the dashboard, and also doing the physical touch may take time, and we would like to reduce this physical touch duration by using eye gaze, or by virtually predicting, or through virtual touch, or predicting where the user is intending to touch. And by that way, we would like to reduce the time required for the user to taking eyes off road when he is driving. So in this study, we used a particular automotive user interface. I borrowed it from a Jaguar Land Rover dashboard, and also we took another particular user interface from a Kia dashboard. And the difference between this is that in this case, you can see the buttons are really big, and there are some smaller buttons here. In the Kia dashboard, the central part is showing some console display, while the buttons are really small. So in one case we have big buttons, one case we have small buttons. So, and we try to explore it with respect to different modalities of fusion. So the first one, we explored a technique similar to this Bayesian inferencing, or using maximum expected probability. So here we have eye gaze signal, and we are using a median filter to take out outliers. And then we are considering this eye gaze signal is noisy. So even though I am getting a XY on the screen, but I am assuming that this XY is the mean of a two-dimensional Gaussian distribution, and it's represented in machine by a 2D matrix. And I can select the sigma x and sigma y based on the technical specification of the eye tracker, that what is the accuracy. And I will populate this 2D matrix based on the eye gaze position and accuracy of this eye tracker. And similar thing we will do with a finger movement tracker. So the fingertip position will take an orthogonal 2D orthogonal position of the fingertip position returned from the finger tracking device, or leap motion device in this case. And similarly, we'll take XY and use a least square predictor to predict that where the user is trying to point at. So remember, the eye gaze is calibrated with respect to screen, but the finger movement tracker is not calibrated with respect to screen. So we are using a least square predictor to predict that where the vector is most likely to hit. And similarly, we will assume that there is a 2D Gaussian distribution represented through a 2D matrix, and then we are multiplying these two matrices to get the maximum expected probability. And then we are moving the mouse cursor based on this XY, which has the highest probability, combining both this eye gaze and finger position. And we can also use a prior probability of different targets, but in our experiments we kept it uniform. But in reality, we can also assign some values to it. So targets which has higher probability of selection, they will attract the mouse pointer towards them. And then we are moving the mouse pointer and using target prediction system and selecting the target. So the XY is mapped to one of the targets on the screen. Targets mean one of the screen element or button. And we are selecting that. In another case, we are using a precedence or sequential principle, exactly the one we demonstrated, that we are taking precedence of finger movement over eye gaze. So if the finger movement system detects one finger, we will ignore the eye gaze and we will move the mouse cursor based on the finger movement. And if there is no finger detected, then the pointer will be moved based on eye gaze. And it is very similar to the one that we just demonstrated with this robot case study. Third one is different. Here we will assign different activity to different sensors. So we will move the mouse cursor based on finger movement, that as I am moving the finger, the mouse cursor will move. We will use eye gaze to expand target or zoom in part of the display. So wherever the system believes the user is looking at, that part will be zoomed in, and then the mouse cursor will be moved through finger movement and we will select target. So we compared these three different fusion strategies. We designed a dual task study. Dual task study means that here the user are performing two tasks simultaneously. That the primary task was driving using a driving simulator, and secondary task was point and select, which was initiated by a auditory signal. So the user is driving, and when he or she is hearing this beep sound, she has to look down and select the target. And we make a repeated measure 2x4 design that we use two screen layouts and 4 different interaction strategy. So use the just default touch screen as a control condition, and then these 3 different finger eye movement tracking strategies. So this was the task. Let's see if it plays right. So this is the experimental setup. So she is driving here, and this is the secondary display setup on her side. And this is the eye tracker, and here is the lip motion controller, and she was selecting. And this is the experimental task that it's a driving track of a game, and she has to make a round through this. So first, yeah, let me see if we can play this video. Okay, so it's let's move on. So the first we compare the average driving time of the full circuit in different conditions. So on the x-axis we plotted these 4 conditions. Touch screen is the lowest, and what we noted that the lowest time was with touch screen, which is sorry. The lowest time we attain with touch screen, which is not unsurprising because users are using touch screen on everyday basis. But among these 3 fusion strategy, that when you're using this Bayesian model, so that generates the lowest driving time for both the simple screen, which means that Jaguar Land Rover screen, which has big buttons, and also for the complex screen, which has this Kia dashboard with small buttons. And in most cases, the driving time was more when for the complex screen when the buttons were small. We also measured the average cognitive load measured in terms of NASA TLX score, and again the minimum was obtained for touchscreen, and again the minimum one was obtained for these Bayesian fusion strategies. But when we are comparing the average number of target selection, then it's interesting to know that for the fusion strategies, the average number of target selection is lower compared to the other 2 strategies. And for the screen with bigger buttons, we almost see no difference. So users can select all the targets. But when the screen elements are smaller, then users selected the most of the target when they use the finger tracking with zooming technology. And similarly, when we compare the errors also, the multimodal fusion strategy has more errors compared to the other strategies. And similarly, the average response time, or that means the how much time this took to select one target, that was also highest in the multimodal fusion strategy compared to the multimodal strategy, in which case they were using either eye gaze or finger. So it's in summary, we have slightly confusing results that using eye gaze for pointing either reduce driving time or reduce response time than only using finger tracking system. But we still do not have or did not have the best fusion strategy, because the Bayesian fusion improved driving time and reduced cognitive load. But the naive multimodal system, which was using this precedence principle, it reduced the pointing and selection times. And the latency in the finger tracking system reduced its utility as a pointing modality. So what do we mean by that? So the eye tracker, whenever the users use, in this case, since it was a dual task setting, the user was not constantly looking at the screen. So the user is looking at the primary driving screen, and occasionally when they are hearing the beep sound, they are looking to the secondary display, just as we do when we are actually driving. Now the eye tracker that can instantly detect eye position and started tracking. But the finger tracking system, the users need to put her finger on top of the finger tracking system for a while for the finger tracking system to detect the finger position, and then it started working. And this minute delay, which is not recognizable when we are using it for a single modality of use, that becomes quite predominant in this setting, because the user is holding the steering hand with two hands and then taking one hand and trying to point towards the screen. But this latency in finger detection actually make the finger tracking a worse modality. So in this case, although these results we are talking about eye tracking or finger tracking, but you should note that these results are actually translating to the particular technology or particular device we used for eye tracking or finger tracking. So if we have a better finger tracking technology, say we have a wearable finger tracking technology, in that case, probably we can get rid of this latency, which we did actually in a much later study undertaken here a couple of years ago. So we recorded actually the eye tracking and finger tracking more coordinates when the user is not using them for mouse cursor control, but just using the touch screen. And surprisingly, we found that when users are using the touch screen normally without bothering about eye tracking or finger tracking, in 90% of the cases when the users are touching the target, the lip motion sensor failed to track finger movement because it couldn't start tracking finger by the time users touch the screen and bring his hand back. Next, we kind of further use this precedence-based fusion strategy, that eye tracking and finger tracking, for this head-up display or head-mounted display system. And here also our challenge was that using this using eye tracking for controlling a pointer on a projected display. So he or she is trying to play music with eye tracking, and you can hear the music. And now we will. It also has this distraction detection feature.
Look back. Okay, now close your eyes. Okay, open.
And the same system we also used with finger tracking. And some of the challenge was in terms of placing the eye tracker and then combining these two modalities. And the display surface was not flat as with a screen, and these trackers were made for tracking eye gaze on a screen. So we have to intervene something so that we can track eye gaze or finger movement on a reflected display on the windscreen. So what was our prospective solution? That we used a neural network model for converting the raw eye gaze coordinates into coordinate position on the windscreen. So it's again in computer vision technology, it's something called model or view transformation, that where we convert one screen coordinate system into another screen coordinate system. So we compared both linear regression based model and the neural network based model, and we found that the neural network based model has less RMS error and more correlation and R square value compared to the linear regression model. And it was a just 3-layer feed forward artificial neural network, and using that we convert the raw eye gaze coordinates into coordinates on the windscreen. And then we also used a target prediction technology to find the nearest target to the predicted eye gaze movement and activate that target. Activate means we changed color of that target and the user selected by a mouse click, and the mouse was connected with the steering wheel. Later implementation, we used the push button switch. And same thing we also did for a head mounted display system, in which case we, instead of a screen mounted eye tracker, we used the eye tracking glass, and similarly we converted the XY coordinate to a flat screen, and we can also control a screen cursor on the screen from the coordinates recorded in a eye tracking glass, which is 3-dimensional coordinates, and later on we used more sophisticated model to take care of also of the head movement. And similarly, we compared R-square values for predicting XY values on the screen using both linear regression and neural network model, and we found the neural network model worked better. And again, this is a similar demonstration where we are controlling the screen pointer on this TV using these eye tracking glasses. So wherever he is looking at, and this crosshair, the crosshair is moving based on his head movement, and within this region, the pointer is moving, and one of these 5 targets is being selected based on his eye gaze movement. So here, actually, in effect, we combine both head movement and eye tracking simultaneously, and then he can switch to this multifunction display where we have the screen-mounted eye tracker, and he can control a screen pointer here using this eye tracker instead of this eye tracking glasses, or using the screen-mounted tracker. So we made this demonstration in the Aero India 2019, and later on that was also covered in 2020 by New Scientist, which is one of the leading science journal now. And presently we are also working on developing our own indigenous eye tracker through which we can do the same activity, not using a commercial screen mounted tracker, rather a webcam based tracker. So maybe in a later lecture you can see such a demo, or you may already have noticed seen in our lab that we can do all these things with our indigenous eye tracker instead of the commercial eye tracking system. Right. So this particular case study, it will show you a medical collaborative robot developed during this COVID pandemic, and to safeguard medical professionals when they take vital measurements like temperature or pulse oximeter reading from patients. So we ran a sample trial at the Institute Health Center, and here you can see that the cobot can be controlled using a video see-through interface using the laptop, and here the person can see the patient in front of him, and he can do close inspection using the camera module, and also he can take temperature. There is also a pulse oximeter module below here where the person can put his finger, and the whole process can be run by maintaining social distancing with the patient, or we can also put a screen in between the robot and the operator. And we also demonstrated the user interface to doctors and collected further requirements from them, which will improve the user-centered design process, or will part of the user-centered design process. And the device works with legacy instruments. So in our lab, we developed bespoke grippers, and also we update a commercial low-cost robotic arm with appropriate servo motors to make it operational with legacy instrument. And then we developed the user interface, the electronic circuitry part, to operate this temperature gun and the camera module. So this particular situation is seeing that when the doctor is sitting in the same room with the patient, but we also created a virtual reality tele-robotic solution where the doctor is situated in a remote place or is not co-located with the patient. So he can control this robotic arm using the hand controller of a virtual reality headset, and he can immerse himself in the same place where the patient is. So the doctor can see this room inside this virtual reality headset, and we also put a canvas where we can showing the live video stream. So when the doctor is want to do close examination or the faces of the patient's face, that reading facial features like looking at eyes or facial symmetry, throat, etc. So we put the live video stream here. So in this video, this is the doctor who is donning the VR headset and operating the robotic arm with this handset. And here is the patient. He can be in a different room or in a remote place, and he is sitting in front of the robotic arm, and the whole robotic arm will never touch the patient, and the patient all need to do is lean towards the robotic arm when he is taking the temperature reading. So presently the system is under evaluation through its end users. And this is, you can also take another example of using augmented virtual reality system to control robotic arms. So in the case study 3, we will take a digital TV framework, and here the situation is a bit different than the previous cases. In all previous cases with car or aircraft, it was one-to-one interaction. That one operator is operating one screen or device or something. But in our digital TV, that multiple persons will watch the TV together, and it further complicates this fusion system. So this particular case study coming up from this European Union Guide project. Here Guide stands for Gentle User Interface for Disabled and Elderly. So it was funded through a European Union FP7 program in 2010 and ran till 2013. And still now we are using some results of this project for developing a new ITU recommendation. And here we try to develop a middleware which will run on a set-top box, and it will support multiple modalities like gesture, voice commands, remote control, audio, virtual characters, text-to-speech controller, etc. And also it will support a second screen. And remember that it was done in 2010, so that time these HBB TV or smart TVs were not very available, or research was still going on even on Google TV or Apple TV. So we also took an effort to develop such a framework. And many of these systems now it's commercialized as smart TV or Apple TV, or in Europe as hybrid TV. So here we will mostly look at the conceptual framework on the multimodal fusion and fission strategies. So my colleagues at the University of Lisbon, they mostly worked on the fusion and fission strategies. And I was in Cambridge that time, so I mostly worked on the input interpretation and this context and user model part. So how it works, it was like that the input interpretation and adaptation module, it will work as an initial filter, and it will filter out noisy signal, that it will remove jitter from a remote control device which has inbuilt accelerometers, and it will process speech signal and denoise speech signal. And similarly, when the user is using a second screen device or any modalities like eye gaze tracking or finger tracking, so it will denoise this signal and do some initial processing and adaptation, and send to the fusion module saying that what the user is trying to do, that he is trying to point. So it will do this mapping from the raw input signal to some device action, and that will be sent to the fusion module. So it used a frame-based system, that it had individual frames for different input modalities, and it will send all this input signal that the user is uttering a keyword, the user is pointing the remote like a laser pointer towards the screen, or the user is using a second screen device. All this input it will send to this dialog manager, and this dialog manager will talk to the application layer. So this part is running on a middleware, and the dialog manager is responsible to communicate with the application on top. So the application can be a broadcast program, it can be just a web app, it even can be the user is taking part in a chat show and giving some input, anything. I mean, a user is taking part in a reality show, and which requires him to give some input to an online system and so on. So the dialog manager will communicate with the applications on top, and the application in terms will send some response to the dialog manager, which it will send to the fission module. And based on this user and context model, the fusion module will prioritize the input, that whether to give priority to the voice input, whether to give priority to the remote control, or whether it is need to two modalities need to be combined, like the user is moving the mouse pointer, sorry, the remote control like a mouse pointer, and also clicking that or selecting a button in that. So both input, the press and the movement, both should be registered. And similarly, based on the user model, which also record the level of range of abilities of user, the fission module will decide that which are the modalities it should show output, that whether it should add a subtitle, whether it should show some avatar, or whether it, if possible, that it should invoke any haptic device on the second screen device, and so on. And then the system response will be given to user, and the user will give input, and this cycle will go on. And the whole system will run on this guide core or the middleware. And third-party developers, they can use the APIs either through deploy it on the set-top box platform, or they can deploy it as web-based system, and they will leverage this multimodal fusion and fission strategies implemented on the guide core. So this is one demonstration of the system. So I will keep the sound on, so you can check this out. So first it will showing a video conferencing feature. So this is the broadcasting program in background, and they are overlaying this semi-transparent web display on top of that for.
Hi, Benny. How are you?
I'm fine, thanks.
Your new house seems really fancy, huh?
Yeah, the company's accommodations seem to be really high-end now.
And how do you like it in Berlin?
Yeah, it's a nice city actually, and
just hold on for a second. I need to check something on my TV.
yeah, okay, you know what? I'm just gonna check my food.
So they are trying to show that you can minimize the.
Listen, I
video
think I need to
conferencing
get back to cooking now.
and-
So
Oh, that's all
talk
right
to you
then.
later, maybe.
I think I will also go then. Take care, man. All right? Bye-bye.
Yeah, all right. See you. Bye.
On this screen you can select Start, Help, Login, Settings, Call, Store Number.
Guide settings.
So the system was also controllable through hand gesture, and later I also create a case study of controlling the same thing with eye gaze. So and remote and our technical partner was Technicolor, so they also gave us a remote through which has you can use like a laser pointer. So this is the user profile creation application.
My name is Guide. In the next few minutes, I will tell you about your new TV. I will also help you adjust it to yourself.
The pointer on screen shows where you are aiming at. When you point at a button, it
So
gets highlighted.
using this
To select
functionality,
it,
I am just
press the
reducing
O-
the sound. So using this application, we created the user profiles. Like here, you can see the Ishihara color blindness test, or which can detect difference between protanopia and deuteranopia. And this user profile played a key role in this fusion strategy, because it helped to the machine to decide that which modality will get precedence. Say, for example, a user who has severe visual impairment. So for him, we will give more precedence to the voice command compared to the hand movement command, and similarly vice versa. And and also it helps on the adaptation profile, that if we notice that some user has difficulty in or spasm or tremor in finger movement, so the input adaptation model adapts accordingly, and we that in turn dictate that the target prediction technology, and help us to decide the response from the user. So in the fusion module, we remove this jitter, that if we already know from the user model that the user has tremor in finger, and rather the input adaptation module send the predicted button or screen element where the user is trying to point at. So anyway, you can we still maintain a website, or the European Commission still maintain a website on this system. But to summarize today's presentation, that we introduce you to multimodal systems and various fusion strategies. We looked at case studies of using modalities using eye gaze, finger movement, speech, and text-to-speech output. And also we looked at to evaluate multimodal systems, that one part is the development part, but the next part is the user evaluation part. And as you noticed with this automotive example, that the user evaluation many times can highlight inaccuracies or latencies or mismatch of latencies among different modalities. And many times we may not come up with a clear answer that which is the best fusion modalities, which can further lead to further research and development work. And only the fusion strategy, that's how, is not good enough. Rather, the user evaluation that can lead us to develop further effective and useful multimodal systems.